In this video, we're going to be looking at the concept of circular motion and centripetal acceleration. What are we going to do? We're going to review the difference between rotational motion and circular motion. We're going to apply Newton's first and second laws of motion to circular motion. We're going to define and calculate centripetal acceleration. We're going to address the misconception and lie of centrifugal acceleration, as well as explain the differences between centripetal acceleration and angular acceleration. We will also relate centripetal acceleration of an object to that object's tangential speed in a circle, and we'll also relate that centripetal acceleration of an object to that object's angular speed as it moves around in a circle as well. Why are we doing this? Because circular motion is a very common form of motion that's in the universe, and understanding this kind of motion was key to our development and understanding of gravity, as well as how the universe operates. Most people also have no real understanding on how and why objects move in circles. There are a lot of misconceptions out there that have just been accepted, and they often cause large amounts of confusion when things don't act the way you thought they did, because you didn't understand the situation in the first place. So let's first take a look at the differences between circular motion and rotational motion. We've looked at this in the past, and we're just simply refreshing this concept. When something moves in a circle, it moves around a point that's not inside them. So here we have a satellite orbiting the Earth, and the center of the satellite's motion is along the axis of the Earth itself, not through the satellite. We can actually trace a path of the satellite to make a circular shape. If I was to just isolate a point of time where I see the satellite, by simply circling the satellite right here, I can see the satellite moves out of that circle. I can see that it's actually traveling. And again, that's how we get this circular trajectory or path. However, if something is going through rotational motion, then it rotates around a point or an axis that goes through their body. So when we look at just the Earth, we can see that the Earth rotates through an axis, or rotates around an axis that is through itself. If I was to circle the Earth, I would see that the Earth never leaves the circle. It's not moving tangentially, it's moving rotationally. One of the reasons why people will get confused about rotational motion and circular motion and get them kind of switched around is the fact that these two do have a relationship. For example, if I was to focus on just a piece of land on the Earth and track its motion, ignoring the rest of the planet, I would see that this piece of land would in fact travel in a circle around the center of the Earth itself, or at least in a circle around the axis of the Earth's motion. So there is a connection between the rotational motion of a solid object and circular motion of any point on that object that is rotating. Likewise, if I look at the satellite going in a circle around the Earth, while I do see a point, which is the satellite moving in a circle, I could instead focus on the radius. And I can see that over a period of time, the radius sweeps through an angle. So I could actually view the satellite as a point on a disk that is rotating. So instead of a hollow circular path, I could pretend that this is a solid disk that is rotating, and the satellite is just a point on that disk, much like a point on the Earth's surface is just a piece of a solid object that is rotating around its own axis. So this is something that can confuse people a bit, and I can always view circular motion in an angular sense if it's more convenient. Just like I can often think of rotational motion in a circular sense if it's more convenient, but I do have to be careful that I'm not applying the properties of each one of these when it's not appropriate. And what do I mean by the term properties? I'm referring to how Newton's laws relate to this kind of motion. If we take a look at Newton's first law of motion, it states that an object in motion or a system in motion keeps that motion constant. There is no change in speed or direction unless there is a net external unbalanced force acting on them. So here I have a person again sliding on ice, and there is a force of gravity pulling down on them. There is a force of the ice pushing upwards, but there's no real friction or other force there. And so this person moves in a straight line with a velocity that is relatively constant. If we were to apply Newton's second law to this motion, we would say that the net force is zero. So I have 0 newtons of force acting on this person. So that must equal the mass of the person times their acceleration. And if there's no force, there's no acceleration, and so there is no change in their motion. If I'm looking at a car that is accelerating tangentially, then I could see that the speed of the car changes. Their direction doesn't change, but their speed does. They travel a greater distance every second than the second before because they're speeding up. And we could turn around and say that the net force on the car, such as the friction force, force on car, must equal the mass of the car times the acceleration that the car experiences. So force on car must equal the mass of the car times the acceleration that the car experiences. But please notice, Newton's second law doesn't say that it only has to be a change in speed. There's the option for or direction. Remember, acceleration is a rate of change of velocity. It's how fast your velocity changes. But velocity is both a speed aspect as well as a direction aspect. So I could actually have a constant speed and change direction, and that only happens if there is a net unbalanced external force acting on me. This is a key thing that leads to our development of gravity that we'll talk about in a little bit. So the truth is, we actually have three kinds of accelerations that we're going to focus on in this course. We've already looked at two of them. We have the tangential acceleration, where objects speed up in a straight line. This only happens when there is an unbalanced external force acting on the object or system, and we can turn around and use Newton's second law, where the net unbalanced force is equal to the mass of that system times the acceleration of tangential of that system. When an object has a constant tangential acceleration because of a constant unbalanced force, the object follows the rule of odd numbers, where the distance it travels in its first interval is going to be 1/3 the distance it travels in the second interval. And that distance of the first interval is 1/5 the distance traveled in the interval after that next interval. So the distance I travel in the first interval is x, then my next interval will be 3 times my first distance. Then my next interval, I go 5 times that first distance. If I go for another interval, it'd be 7 times that first distance. And this is how we get that exponential growth, which is formed by the rule of odd numbers. We also turn around and say that my tangential acceleration is equal to the change in my tangential velocity over time. And if the object moves in a straight line with no change in direction, we often get lazy and talk about change in speed over time rather than velocities, which is a very bad habit because when I change directions, it becomes very confusing. So we specify velocity. The next the next type of acceleration that we looked at was the angular acceleration. This is how the rate at which a disk or something rotates changes the rate at which it's rotating. This happens when I have a net unbalanced torque. So this is different than forces, where this is an unbalanced force, which is a straight thing that pushes you or pulls you. This is an unbalanced thing that twists you instead, causing a change in angular motion. But please notice, it only happens if I have an imbalance. The rotation follows the concept or equation that the net unbalanced torque is equal to the moment of inertia of the system times the angular acceleration of the system. This is not Newton's second law, which is the net external force equals mass times acceleration. But torques are a twisting influence trying to create change, while forces are a pulling, pushing influence trying to create change. They are similar in their function. Mass is known as inertia. I is the moment of inertia. These are both how you resist a change in your motion. And accelerations are how fast changes take place in your motion. So while this is not Newton's second law, we do see commonalities. We also see commonalities in how the displacement of the object changes over the passage of time. The spinning object, if there is a constant external torque and has a constant external angular acceleration, also follows the rules of odd numbers. The distance that I travel in my first second compared to the distance in my second second would be 1/3 the distance in my first. So I travel 3 times farther in my second interval. In my third interval, I would go 5 times the distance I did in my first. 7 than my first and my next interval. I have the same progression for angles that I do with tangential distances for an object with a constant tangential acceleration. And the equation is the change in angular velocity over time, while for tangential acceleration is the change in tangential velocity over time. Again, we have a lot of commonalities. It's just really a difference in names and units, but the relationships for everything here are pretty much exactly the same. And that all makes sense. But now we have another type of acceleration. This type of acceleration is dealing with objects that are moving in a circle, such as the satellite going around the Earth. In this case, we do have a net unbalanced force, just like we have in the first case, but with one very important difference. If I take a look at the motion of the car, the net unbalanced force goes with the velocity or against the velocity, which means this force will affect the speed aspect of the velocity. So I will either make you speed up or slow you down. The velocity here on the satellite is going perpendicular to the radius of the motion of the satellite. It is tangent to the circular path. But the force of gravity is pulling along the radius. This force is not actually helping the velocity or fighting the velocity. It is simply changing the direction of the velocity. When I'm dealing with this kind of acceleration, the rule of odd numbers does not apply. The distance I travel in my first interval could be the exact same distance in my next, and my next. If I'm looking at this from an angular perspective, then the angle that I travel in my first time interval would be the exact same angle I travel in the next, and then possibly the next, and possibly the next. Again, this force is not actually affecting the speed of the motion. So I can't really use the same kind of equation that I used with the other accelerations. It is still by definition how fast the velocity is changing, but I can't solve it algebraically the same way because I'm not dealing with change in the values of speeds. If I was actually just to try and use values of speeds, I would actually come up with an acceleration of 0, which is totally inaccurate. Now, it is this type of motion that allowed Newton to develop his concept of gravity and his concepts that allowed us to figure out how the universe operates. It was already known long before Newton, back from the dawn of man when he started to first make observations, that things in the sky seemed to move in circles around one another. The big question was, who moves around whom and how and why? Those were the big mysteries. Galileo, Kepler, Aristotle all had models to predict or show what was happening, but none of them could explain. Before Newton developed his concept of gravity, he had already come up with his 3 laws of motion based off the work of Galileo. And remember, the first law was that an object in motion or a system of motion does not change in its speed or its direction unless there is a net external force causing that object to change its motion. And he knew that the net external force on the object must equal the mass of that object times that object's acceleration. And since objects have to change direction to go in a circle, there must be a force pulling that object towards the center of the circle, because the velocity goes in this direction and then goes in this direction. There's a change in this. So this is my v initial, and this is my v final, and this is the change in my velocity. This means this is the direction of the acceleration, which means the force must be pulling towards the center. Now, Newton did not know that this was gravity. He had not developed such a concept, but he knew that there was a force that had to be pulling these things inward. So some sort of mystery force, and he had named it the centripetal force, or at least we named it the centripetal force because it pulls inward. We can calculate the centripetal force through Newton's second law if we know the acceleration and mass of the object. But this also means that we could find the mass of something if we knew the pulling force and measure the acceleration. Many people get confused by the types of forces that act on an object that moves in a circle, because many times people hear something called as a centrifugal force rather than a centripetal force. You often hear how when there is a turn, you get pulled to the outside. If you had taken a biology class or a chemistry class, you might have seen something called a centrifuge. This is a device that's used to separate solids from liquids or to separate liquids of different densities. It's often described as the following. You place this mixture inside a test tube. The test tube is spun in a circle, and everything that is really heavy is pulled to the outside, and all the lighter stuff is kept on the inside because it doesn't get pulled out as hard. It's kind of like how people describe a washing machine. You have all the holes on the side of the drum. And when the clothes enter the spin cycle, the clothes and the water that are inside spin in a circle, and the water is pulled out of the clothes so they get kind of pre-dried a little bit before they go into the dryer, because fabric holds a whole lot of water. So we spin them to draw the water out, and so the water gets flung out, it's pulled out, and the clothes are a little bit drier. We can even talk about how we have this girl here that's on top, that's attached to this ride at the playground. There's a boy that's spinning in a circle, and she is being flung around. And you can easily see that her feet are off the floor, and it looks like she's being pulled outward. And this is what we call the centrifugal force. And you'll hear people talk about this constantly. In fact, that's why this is called a centrifuge, named after the centrifugal force that seems to be pulling all of the stuff to the bottom of the test tube. The only problem with the centrifugal force and concept is that it's totally and completely and utterly wrong. It does not really happen. If we go and take a look at the satellite orbiting the Earth, again, we know that the velocity is changing going around the Earth, and so there must be a force that pulls inward on the satellite. But when we take a look at a situation like this, how can the girl be flung outward if she is being pulled inward? And that is because of inertia. Think of it this way. If we were to pause for just a moment where the girl was spinning, and at this particular moment in time, the girl was to let go, what would happen to the girl? Where would she fly out? Would she fly outward like so? Would she fly inward? Would she go back? Would she come at some angle? Would she go straight back? This is something I want you to think about for just a moment. So when this girl lets go, where would she fly off? If you need to, pause the video for a moment, come up with an answer, and then simply hit play again to resume the video. Now, we're not going to actually have a little girl let go from a ride like that and have her risk getting an injury. But we do have many examples where something is moved in a circle and then let go. If we take a look at the case here where we have this little boy who is throwing a baseball, if you notice when the ball is in his hand, the ball follows an arc motion. That's because his hand is holding on to the ball, pulling the ball towards the center of the arc. However, the boy lets go and the ball flies. The boy lets go right next to his head. His palm is facing forward, and the moment he lets go, you can see that the ball flies in a forward direction. The ball has inertia. It's in motion in a straight line when the boy lets go, and it will maintain that direction unless there's an external force such as gravity pulling the ball potentially downward. But the reality is there is no outward force. If the boy had done that, then when he lets go, the ball should fly upward. Here we have a person who is throwing what is known as the hammer throw. Basically, the hammer throw is a ball attached to a chain where you spin the ball in chain in a circle, let go, and it flies off. Now, if you notice, when the man is spinning, it's easy to think that the ball is being pulled outward because he is pulling so hard inward to keep the ball in a circle. It is this outward force that we call the centrifugal force. But the truth is, there's no force there acting on the ball. The man is pulling inward on the ball. We call this force, this inward force, the centrifugal force. Now, if the man pulls on the ball, so this is the force on ball from man, then there must be a reaction in the man-ball system. And the truth is, the ball is going to pull on the man outwardly. This is the force on the man from the ball. That is the centrifugal force that people talk about. But it's not on the ball, it's actually on the man. And that's because the man exerts a force on the ball inward. Please notice that the moment the man lets go of the ball and his pulling force is gone, the ball flies off in a straight line. The man lets go of the ball right about over here, and you can easily see that that ball goes where there is no netting in that direction. If there was a centrifugal force pulling this ball outward, then when he lets go, that force would fly the ball into the netting. So when we see this girl here with her feet up, it's because her body is trying to go in this direction. But because she's holding on to the banister, her body's being pulled this way. So this is where the force is, this is where the velocity is, and this is where inertia is going to have her body go. The concept of the centrifugal force is an illusion. And if this girl was to let go, just like the baseball and the hammer flow, she would fly off in the direction tangent to the circle, perpendicular to the radius, and not outward. This is a very hard concept for people to grasp because we see the girl's feet go up, we see the man having to fight the ball. It's easy to think that there is a force pulling them outward, which is acting on the object that's moving in the circle, pulling it outward, but it's not. We are only experiencing the reaction to the force of the object, the reaction to the force that's pulling the object inward to the center of the circle. So, centrifugal, the misconception title that we often see, means centrifleeing. This is that misconception that objects are pulled outside of the circle. Again, it is really just the effect of inertia trying to maintain a velocity that's tangent to the circle itself. It is, if you want, the reaction the puller experiences from the object that's being moved in the circle. Because since the puller pulls on the object moving in the circle must pull back. That is the third law of motion. Centripetal means center seeking. It takes a trip to the center. So centripetal means center seeking. That is the true direction, the true type of force that acts on any object that is moving in a circle. Now, if we're going to understand how Newton was able to come up with his laws of gravity and how they apply to the rest of the universe, we need to first take a look back to see how the concept of the universe had evolved. So if you remember, back in the beginning, when we had Aristotle, it was viewed that everything moved in a circle around the Earth. All stars, all planets moved in a circular motion, and that's because they were made of an element that could never be found on Earth that caused them to move in a circle, while everything on Earth was made up of one or a combination of four basic elements of fire, earth, air, and water. Each element had its own realm, and each one naturally moved to their own realm. Anything in space was not of the Earth, thus it would just move in a circle around the Earth in its own realm, which means we would never understand what happens in space because we can't relate or apply to it because it follows a totally different set of rules than the Earth itself. This model was eventually replaced with the models of Galileo, where again, everything moves in a perfect circle, but the sun is the center of our solar system, and everything moves in a circle around it. Galileo was not able to offer any explanation on why things move in a circle. All he did was say, this is the observations that I have made. This is the model that predicts to a better degree of what's happening than what this is. But why this happens, I do not know. Galileo's model is actually replaced later on by the work of a man named Kepler. Kepler's goal was to refine the circular orbit theory to make it more accurate. And although his goal was to show a better model of circular orbits, his work actually led him to conclude that the orbits are actually elliptical in shape, that the speed of the planets actually change as they move around the sun, and that the sun is not in a center, but actually at one of the foci of the ellipses of orbit. Kepler's model is far superior than any other model that was developed, and we still use his model and his laws of planetary motion that he used from his predictions to this day. But unfortunately for Kepler, he could never offer a really good explanation on why this is. They had theories, but none of them were really scientific. They were all rather, from our standards, a bit fantastical. With Aristotle, the theory was just simply elements. This is how the universe behaves. Don't ask questions. There's a whole other element in the universe that doesn't exist on Earth. You can't understand why it does it. It just does it. Accept it. So everything moves in a circle besides the Earth, and you'll never understand why. Just deal with it. That gets replaced with the concepts that perhaps there are crystal domes that each planet is attached to. This was actually Kepler's idea, that there were crystal domes that the planets were attached to, and that these domes rotated, and as they rotated, the planet attached to the dome moved in a circle around the sun. The size of the domes was dictated by geometric shapes that determined the radius of the domes. These shapes were considered the perfect solids, and they are very similar to the shapes that you would see on a set of Dungeons and Dragons dice. Other theories was that there was a complex network of gears and rods, all again made out of crystal. This is significant because the crystal is transparent and you can't see it. But we have these complex arrangement of rods and gears made out of crystal that makes the universe move. So everything has to be physically connected, and everything moves in a circle because of this. Other theories dealt with models that were a little less mechanical, but far more spiritual. If you notice, the planets are all named after gods. And that is because it was believed that the planets were alive, that they were gods, and the gods would move themselves in the sky to either convey a message or to enhance their ability to affect events on Earth. It's one of the root concepts of astrology. Those who are Christian at the time also developed a similar kind of mindset. The early Christian church had turned around and said that the planets were either moved around either by the hand of God himself or by his angels, and that the movement of the planets was his means of communicating his will to everyone else. So kings and the church often had sanctioned astrologers, where they would then look at the sky, see where the planets were, and then say what God wanted. They had a stranglehold on this, because if you were an unsanctioned astrologer, you would be persecuted, banished, tortured, and or killed for practicing heresy. Biggest reason for this is many astrologers can look at the same arrangement of stars and come up with different messages. And if we're going to play that this is the message of God allowing us to do a particular action, such as going to war, then we don't want anyone else coming up saying, well, looking at this, we actually see that it should be something else. Now, during the time of Newton, the world is accepting a very new ideas. And Newton had already developed his 3 laws of motion. And he had noticed on how cannons, when fired from a cannon, actually travel as a projectile. And he had already made the connection that the force that makes an object fall, which is gravity, and he had pointed that out, was also the same force that caused the projectiles to fall. And so that a projectile is nothing really more than a freely falling object. And this is actually where the concept of planetary gravity comes in. See, the big thing about Newton and the concept of gravity isn't that he invented the concept. It's the fact that he was able to take it and apply it to the rest of the universe and explain how the universe works. And there was no apple falling from a tree in an orchard. There was, however, cannons firing cannonballs. And like I said, when a cannonball was fired, it would make a projectile path. And when fired faster, the path would be more parallel to the surface of the Earth and go further. And fired even faster, would be even more parallel. The arc becomes more like the curve of the Earth. So Newton had posed a thought experiment. He was like, well, let's say I was to be on top of a cliff and I at the top of the Earth, and I was to simply drop a ball. The force that makes the ball fall is gravity. If I throw the ball takes the projectile path and hits the ground because of gravity. But if I throw the ball faster, then the projectile will travel a longer distance before hitting the Earth because of gravity. But it curls because of gravity. So what would happen if I was to throw the ball just fast enough that when it curls, it matches the curve of the Earth? Then that object would return to where I am. And if I move out of the way, then that object would then repeat the motion time and time again, always circling the Earth, always falling because of gravity, but never hitting the ground, because the ground isn't as flat as we think, but it's actually a curved spherical-ish type shape. Now, he didn't actually do this. People did turn around and say it's impossible to throw something that fast, but it was the Renaissance where they were open to ideas, and it was a simple thought experiment. And if anyone was to turn around and say that this is insane because there's no way on Earth you can throw something fast enough for it to orbit the Earth, they would be laughed at in modern times because that's exactly how we launch rockets into space to orbit the Earth. We launch them with enough speed so that once they achieve their orbital position, they simply fall back to Earth. But they are traveling in a circle around a circular shape, so they never hit the surface. We always fire our rockets towards the east so that we can actually use some of the Earth's rotation to help us. Because when we fire a rocket, it not only gets the velocity that the engines give it, but also the rotational velocity of the Earth itself. So the tangential speed of a rocket at launch is the velocity that the fuel gives it plus the tangential velocity of the surface of the Earth as it in the direction that it is pointing in when it is fired. So now what Newton says is the following. We know we have a satellite such as the moon orbiting the Earth. That moon is actually falling. According to the first law of motion, the only way it changes direction is if there's an external force pulling on it. By extrapolation of projectiles moving faster and faster, we can see how the projectile will become a circular path around the Earth if it goes fast enough. So the moon is actually being held in orbit by the force of gravity. This is significant in many ways. Not only is it, hey, we know the type of force that's pulling on this, but we can measure gravity on Earth. We can do experiments with gravity on Earth. This is not a mystery thing. This means the stuff that makes up the moon could potentially be the exact same stuff that makes up the Earth. There's nothing special about the moon in terms of its composition for it to move in a circle. And all our physical laws that we understand on Earth actually can apply to the moon and everywhere else. And so that's the key thing. Not only that, but if the moon is falling, then the mass of the moon doesn't really matter in terms of the motion of the moon. Its acceleration would be the same regardless of its mass. So just like in free fall, where I have feathers and bowling balls falling at the exact same speed when there is nothing other than gravity acting on them, the moon itself and anything in orbit will have that same property where the mass doesn't need it to be known. So we can actually then start to find things out about the universe without actually knowing the mass of certain things, because we don't need to know it. This, by the way, is nowhere intuitive. If I have the moon orbiting the Earth and I have a small rock in the same orbital path, the speed of the rock to maintain its motion would have to be the exact same speed as the moon. The moon will experience a greater force of gravity. It has more mass. It will be pulled harder. But the acceleration that the moon has falling towards the Earth would be the exact same as that pebble. Just like the feather has the exact same acceleration as the bowling ball. Because again, acceleration of gravity is equal to the force of gravity acting on the object divided by the mass of that object. Again, this means we are now one with the universe. Everything that orbits something else is really just a falling object. To understand what's going on, to do experiments, to understand what's going on, even if we cannot physically be there, can actually be mimicked then here on Earth. Every law that exists in the universe, every physical law is valid in all locations. So to understand what is happening in a galaxy far, 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 far away, we just have to look at what's happening in our own backyard, because the laws in both locations are exactly the same. This makes us, from one point of view, a little less significant, because now we are not quite as unique, but at the same token, we are no longer isolated and alone. We are now part of the grand scheme of the universe. This also means that we can now start to use the motion of moons to find the mass of planets. We can use the motion of planets around the sun to find the mass of the sun. Think about it. We know the mass of the Earth, the sun, the moon, all of our planets, but how do we know the mass? It's not like we ever went to the sun, put a scale on the sun, and measured it. Okay, that's how I can measure my tomatoes in the grocery store, but that's not how we found the mass of the sun. We found the mass of the sun by seeing how it affected the planets themselves. And we can only do that because the mass of the planet, being the satellite around the sun, doesn't actually play a role in the acceleration. Just like when we take a look at a planet, we can easily find the mass of this planet without knowing the mass of the moon, because the mass of the moon does not affect the acceleration the moon experiences orbiting, because it is actually free fall motion. This also means long ago we were able to figure out the mass of planets, but we couldn't find the mass of the moons. It wasn't until we started sending out satellites to orbit the moons that we could actually find the mass of the moons, because I have to see how you affect something in terms of causing a gravitational acceleration on them to find your mass, because again, your mass does not affect your acceleration in free fall. So we know that using Newton's second law, we could say that the force of gravity that pulls an object in orbit around something such as a satellite around the Earth must equal the mass of that satellite times the acceleration of that satellite. This always works. This is Newton's second law, true for all net force situations, for all forms of acceleration caused by a force. So we could easily find the mass of the moon or the satellite if we knew the force of gravity pulling on it and was able to calculate the acceleration. Likewise, if we knew what the mass of the satellite was and the acceleration, we could actually then go ahead and find the force of gravity created by the Earth. And then knowing that force of gravity, calculate things such as the mass of the Earth. Also, we could turn around and say that the mass of the Earth causes the centripetal acceleration of the satellite. And so without even knowing the mass of the satellite, just because we know the acceleration, we could find the mass of the Earth. But if we do it that way, we cannot use Newton's second law. We have to find the acceleration through some other mechanism, such as with tangential acceleration, the change in tangential velocities over time. But we don't have that really here. We need some other equation. So again, we're dealing with centripetal acceleration. Centripetal acceleration means center seeking. It is always perpendicular to the velocity, so it doesn't affect the magnitude of the speed. This makes it very difficult to find. Fortunately, we do have a way to find it. We're not going to get into the math behind the equation. It is actually very involved. But we do say that the centripetal acceleration is equal to the tangential speed of the object squared divided by the radius of the path. We say speed instead of velocity for the very simple reason the direction does not matter when the direction of the velocity does not matter when calculating the centripetal acceleration. Simple reason for that is we often associate a positive or negative sign for direction, and positive 2 squared is the exact same answer as negative 2 squared. Both come out to be positive 4. So we are only looking at the speed aspect of the velocity, not the actual vector concept. If you were to turn around and say that centripetal acceleration was the tangential velocity squared over the radius, you're also correct. You're going to just square the magnitude aspect and come up with the exact same thing as if you dealt with the speed. So it's not a big deal. Unfortunately, this helps to facilitate and reinforce the concept that speed is just another word for velocity, and it's not. In this particular case, we just don't care about the direction of the velocity. Whether the velocities are going forward or they go backward, the acceleration centripetal must always point to the center. Thus, we don't care about direction of the velocity. The scalar equation for centrifugal acceleration is just tangential speed squared over the radius. Please notice we never state the direction. We don't have to, it's a scalar. But please notice that the acceleration isn't just the letter A, it's got this little c on the bottom to show that it's centripetal. That actually tells you the direction automatically. It's towards the center. If I want to clearly state this as a vector, I simply just restate what the c means and say that it's towards the center of the circle. And that is what centripetal means anyway, center seeking, towards the center. So the truth is, you can really argue that every centripetal acceleration value is a vector value because you state the direction in the name. It's centripetal. Now, if you remember at the beginning of the movie, we had discussed on how circular motion can be related to angular motion and vice versa. And sometimes when dealing with centripetal acceleration, it might be more preferable to view something as a rotational system than a circular system. For example, here we have an amusement park ride where people are moving in a circle around a center rod by way of a chain that's attached to a rotating arm. Now I can describe these people's motion as a tangential velocity of meters per second going around the circle. So I can very easily find their centrifugal acceleration by going tangential speed squared over the radius. However, I may not want to deal with the circumference of the circle and figuring out how far they are traveling in meters to calculate their speed. I might consider it easier to deal with the radius arm going around a complete circle so many times a minute. I can work with their angular velocity. Remember, the relationship between angular velocity or angular speed and tangential speed is the radius. Your tangential speed on a circle is equal to the angular speed of the circle if it was to rotate times the radius. If I take this relationship and substitute it in for my tangential speed, I come up with angular speed squared times radius squared over the radius, which simply reduces down to my centripetal acceleration equaling my angular speed squared times the radius. So instead of having tangential speed squared over the radius, it's angular speed squared times the radius. The scalar equation would just simply be angular speed squared times the radius. Vector would be stating towards the center. And again, if we're saying that it's centripetal acceleration, we are actually indicating it's towards the center anyway, because it only points in that one direction. Something that we need to really point out here is the fact that my accelerations can only be positive in mathematical sign. Anything squared is in fact positive. A radius is always positive. So my centrifugal acceleration must always be positive. This means I do not have freedom of choice when looking at, do I make acceleration positive or negative? Anything pointing towards the center of the circle must be positive because the accelerations will always be mathematically positive because it can never be solved as a negative mathematically speaking. So the bottom line is we have two equations for centrifugal acceleration that we can work with that will always yield a positive answer. So anything going towards the center must always be positive. Anything pointing out of the circle must be negative, and anything that's tangent to the circle is neither. We aren't worried about it. We're going to square it anyway. It plays no impact. The big question that people will often have is, which equation do I use to solve my problem? And that answer is really both equations work at all times. It is actually mathematically impossible to not be able to use both equations. If I give you a situation where I give you a tangential speed and a radius, you can very easily say that my tangential speed is equal to angular speed r, and solve for your angular speed saying v over r, and then use your angular equation for centripetal motion if you wanted to. Why would you want to do this? I have no rationale why you'd want to, except perhaps you really like working with it, or you're very angry with yourself, because it just seems like a lot of extra work for most people. But if you find it easier, if that's how you process, then that's awesome, and then that's what you could do. It's an option. Likewise, if I was given just the angular speed and the radius, where I was told something rotated 13 RPMs with a radius of 5 meters, and I was uncomfortable working with radians per second, I could find my tangential speed first by converting RPMs to radians per second, multiplying that by the radius to come up with my tangential speed, and I would then be able to solve using my tangential speed equation. Both of these equations are given at all times, and so there's never an issue of having to have one memorized. They're always given to you. You just pick the one that you want to work with. The only other question that people have or problem is, what is the unit for the centripetal acceleration? Well, the truth is, regardless of the equation that you use, the acceleration's unit is meters per second squared. That is the acceleration unit for the metric system when dealing with meters and seconds, regardless of the type of acceleration. The only acceleration that doesn't have this, that has to be in radians, is your angular acceleration. So centripetal acceleration, tangential acceleration are always in meters per second squared. I hope this is making a little bit of sense to you guys. If you went through this video and you're thinking you have a pretty decent handle on this and that you'll be able to solve problems in class, you are ahead of the game. If you're looking at this thinking, I really wish we had a little bit more on this, I'm almost getting it, but not quite, you're right where you need to be. If you're looking at this video going, I know he's trying to communicate, I just don't understand a thing that he's saying, that's totally okay. You need to get this stuff down, but in the next couple of weeks or months even. So you have time to develop this. And again, these videos are not being used to get me out of teaching, so we'll address any and all concerns you have in class. The purpose of the videos are for you to get exposure to the concept before we actually use it in class.